everyone. I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about diffraction due to end slits using a diffraction grating. So we have seen the brief module of 4, that is Huygens principle, superposition of waves, Young's double slit experiment, expression for fringe width, and Newton's rings. In our previous lectures, we have discussed in detail about single slit and double slit. And today we are going to discuss diffraction due to end slits, if the number of slits are n. So to understand diffraction grating, it is very important to quickly recall what we have seen in single slit and double slit. So using a diffraction grating, which is nothing but diffraction due to n slits, we are going to observe the phenomena. Now how we are going to discuss today's topic is, first we'll see and understand what a diffraction grating is. So in a grating, how we are getting n slits, and then what is the expression for the intensity of the pattern that is obtained due to n slits, then the condition for principal maxima and secondary maxima. Now first thing is diffraction. So a wave passing through a small opening will diffract. Now if we take a plane wavefront, and if this wavefront is incident on a surface which is having a small opening AB. So the light is incident on this plane, and there is a small opening. So the light, when it passes through the opening, what happens here we see is waves traveling in directions other than the direction of the original wave. So what is the direction of the original wave? This is the direction of the original wave. So we have waves in this direction, and in addition to this, we also have waves traveling in directions other than the original wave. That is what we are observing in diffraction. Now how it happens? Why we are seeing the waves in directions other than the direction of the incident wave? It is because light bends around the corners of the obstacle, and then it enters the geometrical shadow. That is what we call as diffraction phenomena. So what is diffraction? It is nothing but the bending of the light ray around the corners of the obstacle and entering into the geometrical shadow. So what should be the size of the obstacle? The size of the obstacle should be very small. It should be comparable with the wavelength of light we are using. So only in such cases where the size of the obstacle is very small, we will be able to see the diffraction pattern. So that is why in nature, even though there is diffraction occurring due to large objects, we will not be able to see it. Now, due to diffraction, what we get is bright and dark fringes. They form a diffraction pattern due to mutual interference of secondary wavelets originating from the wavefront. So this is the original wavefront we have seen. This is the wavefront. Now this is incident on a slit AB. And what we are seeing is at the corners it is going to bend. So whatever rays that are bending, they will mutually interfere with each other. So the wavelets that are produced, each point on this will act as a secondary source according to Huygens principle. And they send out secondary wavelets. And these secondary wavelets will now interfere with each other. And because of this interference pattern, you have this type of pattern on the screen. So this is due to a combination of diffraction, that is the bending of the light, and after bending, the waves from the secondary wavelet will interfere and we will get the diffraction pattern. So in the diffraction pattern, what we have is a central maxima. So the intensity is given, shown by this. And then on either side, you will have minima. This is the minima. And then again a secondary maxima. This is the secondary maxima. and minima. These are minima and these are secondary maximum. Now let us quickly see, because I told you diffraction due to end slits is nothing but a combination of what we have seen in single slit. So one slit, what is the interference pattern? If you understand, then we are going to apply it for n number of slits. So in a wave theory, a plane wavefront is incident on the slit AB. So this is the wavefront. This is the monochromatic source. Light coming from the monochromatic source is made parallel with the help of this lens. So light falls normally on the slit. And each point on AB will now act as secondary sources and will send out wavelets in all directions. And the rays proceeding in the same direction as the incident ray will be focused at O. So these are the rays that are traveling in the same direction as the incident ray. And these are focused to a point O on the screen. So this is the screen XY. XY is the screen. And the rays traveling in the same direction are coming to a point O. Now since they have traveled the same distance, the distance traveled by the ray starting from A and the ray starting from B, the distance, if you see, the path lengths, if you see, they are the same. Because they are traveling the same distance, there is no phase difference. So there is constructive interference. So whenever there is constructive interference, it gives rise to a bright band with maximum intensity. So at the point O, what we get is a bright band with maximum intensity. Now we have already derived the expression for this. We are not going to derive, we are simply going to use the result, what we have seen in single slit. If you want this expression or the derivation, you can refer to the video of diffraction due to single slit. Now the resultant is given by R is equal to A sin nd by 2 upon sin d by 2, where d is equal to 2 pi by lambda into E sin theta. And we also have 1 by n because we are dividing it into n number of slits. So when we substitute for n d by 2, so what happens here? N d by 2 will be n by 2 into 1 by n into 2 pi by lambda into E sin theta. So n will get cancelled, 2 will get cancelled. So what we have in the numerator is only pi by lambda into E sin theta. So this is what we have in the numerator. Then in the denominator, it is simply sin d by 2. So d by 2 is what? You will not have n in the numerator. So 1 by 2 into 1 by n, 2 pi by lambda into E sin theta. So we have 2 and 2 getting cancelled. So we have pi E sin theta by n lambda in the denominator. So if we substitute for pi E sin theta by lambda as alpha, we are making a substitution. Pi into E sin theta by lambda is taken as alpha. So in the numerator, we will write sin alpha, and in the denominator, we have an n. So it is sin alpha by n. And since this alpha by n is very small, sin theta tends to theta if theta is very, very small. So we are taking this as alpha by n. A into sin alpha by n, because alpha n is very small. So I can bring n here. We have NA sin alpha by A, and NA gives the resultant amplitude. R, the resultant amplitude, is given by capital A into sin alpha by alpha. So once you get the resultant amplitude, you can calculate the intensity I is equal to R square. So R square will be what? A square sin alpha by alpha whole square. Now let us go to diffraction due to n slits. Means we have seen that diffraction is nothing but bending of light around the corners of the obstacles. Now how many obstacles we have? We have n number of obstacles. We have n slits. We have seen what is happening with one slit, what is the resultant, and what is the amplitude. So the Fraunhofer diffraction due to N slits we are going to observe now. So what is a diffraction grating? First we'll understand what a diffraction grating is. It is an arrangement equivalent to a large number of parallel slits of equal width and separated from one another by opaque spaces. So in a grating what you have is a number of slits of equal width and these slits are separated by opaque spaces. Opaque means through which light cannot pass. So how it is made? It is made by ruling a large number of fine equidistant parallel lines on an optically plane glass plate with a diamond point. So you take a plain glass plate like this. So what we are having here is we are taking a diamond point and drawing fine lines on this plate. These lines have to be very fine and they are parallel to each other and also equidistant. So what is important here is fine lines, very thin lines. They are equidistant at equal distances and they have to be parallel. So this forms a diffraction grating. Now the ruling will scatter the light and are effectively opaque while the unruled parts transmit the light and will act as slit. So you understood here, wherever we have drawn a line, that part becomes opaque and this is another line, this is opaque. So the distance between the two or the space between the two is transparent through which light can pass. So from these two opaque regions, I say this is A and B. So through which light cannot pass. But the space between A and B is transparent through which light can pass. So that will transmit the light. So what we see here is, so this portion will be the region or the slit. So like this, if we are drawing n number of lines, you will have n number of slits through which light can pass. Now, large number of parallel slits of same width separated by opaque spaces. So 15,000 lines are drawn on 1 inch width of the grating. So if you understand here, we have taken a plain glass plate on which we have drawn these lines. So this is one line and this is one line. So what we see here is the region between the two lines is transparent and that acts as a slit. So these are the lines we are drawing, ruled lines. And then the region in between is the transparent material. So the lines are opaque, we are telling, and the region in between is transparent. Now, how many lines we can draw means 15,000 lines per inch. So we will write it as 15,000 LPI. You should understand this notation. When we write LPI means lines per inch. So nearly 15,000 lines on 1 inch means you imagine how close these lines are drawn. And so the region in between these lines will now act as slits. So the slits are placed very close to each other. Now, the ruled lines are opaque to light while the space between any two lines is transparent and will act as a slit. So how do we measure the width of the slit now? E is the width of each slit and D is the opaque separation between the. So here, if I am taking, this is the slit, this is the line that we have drawn, the width is E and the distance between the two we have taken as D. So what will be the total distance between this line and this line is E plus D. Of course, it is very small, but still we'll have to consider both. This is E and the separation is D. So from here to here, from this line to this line, if you have to measure, that is E plus D, which we call as the grating element. So this we call as the grating element. Now let us understand the theory. It is an ideal grating. When we are talking about an ideal grating, means a grating through which light can pass. We also call it as a plane transmission grating. It is made up of a set of slits of spacing d that must be wider than the wavelength of interest to cause diffraction. We are talking about the width of the slit to be very small, of the order of the wavelength of light. Then a plane wave of monochromatic light of wavelength lambda is incident normally on the grating. Normally here means what? Perpendicular to the grating. What we have seen in single slit. So light comes and falls on the slit normally, and the light that we are taking is a monochromatic light of wavelength lambda. Now each slit in the grating acts as a point source from which light propagates in all directions. So when light falls on the grating and the grating has n number of slits, so each slit will act as a point source. Now, and it will start sending out secondary waves. So after light interacts with the grating, it undergoes diffraction. So here what we need to understand is diffraction, the bending of the light around the corners of the obstacle. So we have n slits means n obstacles. So at n obstacles, the light is going to diffract. And then the diffracted light is composed of the sum of the interfering wave components. So after diffraction, because there are n number of slits giving rise to n number of secondary sources sending out secondary wavelets, and they will interfere with each other and you get the diffraction pattern. And at any given point in space through which the diffracted light may pass, the path length due to each slit in the grating varies. Definitely, if you take one point, other than the rays that are traveling straight, that is in the same direction as the incident light, all the rays that undergo diffraction, means bending, will have a path length difference. There will be a difference in the path length by the time they arrive at a point. Now, since the path length varies, there is a difference in phase at that point from each one of the slit. So we have already understood these two concepts, how the path length varies, and if the path length varies, how the phase varies, because this is a very important aspect to consider whether it is constructive or destructive interference. Now, when the path difference between the light rays from adjacent slit is equal to half the wavelength, means odd multiple of half the wavelength, they are out of phase. They cancel each other and they give rise to minimum intensity, which we call it as dark bands. And when the path difference is lambda, or it's an integral multiple of lambda, the phases will act and maxima will occur. So whenever we are seeing there is a difference in path, if the path difference is an integral multiple of lambda, you will have maxima, that is the bright bands. Whenever the path difference is an odd multiple of half the wavelength, then they are out of phase and you have minimum intensity, that is a dark band. Now, when light is normally incident on the grating, the diffracted light has a maxima at angles given by theta, which is given by the relation d sine theta is equal to n lambda. So, at the central point where they are coming straight normally, they are incident normally, we'll have a maxima and they're governed by this relation, Bragg's law we call it, d sine theta is equal to n lambda. Now, if you see the diagram here, this is the source. We are taking a laser source because it's pointed, it's coherent and monochromatic also. So the light from the source comes and incident normally on the grating. So what in the grating we have? We are having equally spaced slits like this. We have seen how closely they are drawn, 15,000 lines per inch. Now these lines are opaque and the region between them will act as slits. So when light falls on the slit, it will bend. So this is the angle it makes. So all the rays that bend and come here, you will get the first order, n is equal to 1. And which arrive here, we get the second order. The central one is always a maxima because they are traveling straight. There is no path difference, no phase difference. So we get the central maxima. And again, on either side of the central maxima, we have the first order and then second order. This is the pattern we see on the screen XY. So let us now derive the expression. So XY is a screen placed perpendicular to the plane of the paper. So this XY is the screen. This is placed perpendicular to the plane of the paper. Lambda is the wavelength of the monochromatic light we are using. So the light that is coming, this is the plane wavefront we have shown. There will be a source somewhere here. Light coming from the source, with the help of a lens, we are making it parallel and it is incident normally. So lambda is the wavelength of the light. P1 is the point on the screen at which the secondary wavelets are focused. So we are considering the point P1 at which all the secondary wavelets are focused. What are secondary wavelets? Each point on the slit will act as a source and send out secondary wavelets. And these wavelets will interfere and they will form and they arrive at a point P1. So these are the point where the secondary wavelets are focused. And P0 here is the point where we get the central maxima. So this is the point for central maxima, means all the rays that are traveling straight will come here. So the distance traveled by them is the same. So you have P0 as the central maxima. Now consider the secondary waves traveling in a direction inclined at an angle theta with the direction of the light. So if we are considering, if this is the direction in which the ray is traveling, original direction. Now let us consider all the waves that are making an angle theta. So we are going to consider all these rays diffracting at an angle theta. So we are considering those rays. So the combined width of the ruling is called the grating element we have seen, which is given by E plus D. Now the points on the successive slits separated by a distance equal to the grating element are called the corresponding points. So what are the corresponding points? If you see here, the point here and the point here, they are the corresponding points. These are the two successive slits. So here and here, if you see, that is the grating element whose width is E plus D. Now what is the use of this? Where we are going to use? When there is a need to separate light of different wavelengths with a high resolution, then a diffraction grating is the most often tool of choice. So you need to know, when we are going forward to understand diffraction grating, where we are going to use, mainly for the resolution of light. Now, according to Huygens principle, again we'll go back to the basic Huygens principle. Each point in the slit acts as a secondary source and sends out secondary wavelets in all directions. And then according to Fraunhofer diffraction, at a single slit, the wavelets from all points in the slit are diffracted in a direction theta. So whenever there is an obstacle, light falls on the obstacle and it bends around the corners of the obstacle. We are calling it as diffraction. And here we are talking about Fraunhofer diffraction, where we consider the source at far off point and we will use the lenses to focus it onto the grating. And let capital N be the total number of slits in the grating. So we have understood how we are going to draw the lines on the grating, and the number of lines is capital N. And capital N is almost around 15,000 lines, I told, per inch. Lines per inch. So these are the number of lines we are going to draw on the grating. And the diffracted rays from all the slits are equivalent to N parallel rays. One from each middle point of S1, S2, S3 and so on. So S1, S2 and S3 are what? They are the sources arising due to N number of slits. So we have N number of slits. So we consider N number of sources, S1 to so on up to Sn. So all the rays that are coming from these sources will undergo diffraction, and then the secondary waves will interfere and we get the pattern. So now let us see AB be the cross section of the plane transmission grating. So this is the transmission grating AB. Now E is the width of each slit and D is the width of each opaque space. So here if you see, This is the slit we are talking about, slit E, and this is the opaque space. So what is the total length of the element, grating element we have taken as E plus D. So E plus D is called the grating element. Now the points in two successive slits. So we will consider two successive slits, S1 and S2. If you consider, they are separated by distance E plus D and they are called the corresponding points. Now let a parallel beam of monochromatic light be incident normally on the grating. So this is the light that is incident normally on the grating which has n number of slits. Now the points in the slits A, B, C, D, E, F, so on acts as secondary sources. We are calling them as S1, S2, so on up to Sn. They give rise to secondary waves. So all these points, AB is 1, BC is 1, CD is 1 and so on. They all give rise to secondary waves. And secondary waves traveling in the same direction as that of the incident wave, they are focused at O. So all the waves that are traveling in the same direction from here and also from here, if they are traveling in the same direction, are focused to a point O. And they are traveling equal distance, so they reinforce constructively and hence the point O is bright. It is maximum, the intensity is maximum. So all these rays that are traveling in the same direction and reaching O gives rise to maximum intensity, which is a bright point. Now we consider the secondary diffracted rays. Secondary diffracted rays are those that make an angle theta with respect to the normal. So if you are considering this is the ray that is traveling normal, this ray that is diffracted at an angle theta, we call it as secondary ray. So all the secondary rays, this is the angle it makes. So all these rays, the secondary rays, will give rise to diffraction pattern. Now what we are going to do, we are going to draw AM perpendicular to the diffracted beam. So from here, we are going to drop a perpendicular AM onto the next line. So consider the waves that are diffracted at the corresponding points A and C. So from A, if you see the path, and from C, if you see the path traveled by them is the same. Now what is the difference here is only Cm. So the path difference between the waves is given by Cm since they travel equal path beyond Am. So after Am, the path traveled is the same. So the path difference is calculated by Cm. I think this is a better picture to understand what we are doing here. So we have considered 2 points where the waves are diffracting at an angle theta. We have dropped a perpendicular from A onto M. This is the point A and this is the point B. And from this point, the rays are traveling the equal distance to reach here. But the path difference is Cm. Now in the triangle ACM, sine theta. So whenever we take sine theta is equal to opposite side upon hypotenuse. So our opposite side here is Cm upon AC. Okay, so we can write Cm is equal to AC sine theta. AC here is nothing but the width of the grating element, which we have taken it as E plus D. The size of the grating element is taken as E plus D. So Cm can be written as E plus D into sine theta. Now the superposition of waves at P causes interference. Whenever all these secondary waves are arriving at the point P, it gives rise to interference pattern. And what is the condition for it to be bright? P will be bright when E plus D sine theta is equal to n lambda. When it is an integral multiple of the wavelength, we get the point to be bright. That means when n is equal to 1, 2, 3 and so on, all these will correspond to the maxima. Not the principal maxima, they are the maxima. Now sine theta will be equal to what? N lambda from E plus D Sine theta is equal to n lambda. We are going to write the formula for sine theta. So sine theta will be n lambda upon E plus D. So 1 upon E plus D is nothing but capital M. So we can write it as capital N into small n lambda. So sine theta is equal to small n into capital N into lambda. So what is capital N? Capital N is nothing but 1 upon E plus D. Is the number of the grating elements or lines per unit width of the grating. Number of lines per unit width is given by N is equal to 1 by E plus D. Now, after calculating the path difference and the corresponding phase difference, the resultant amplitude in the direction theta. So, we are having the waves that are coming, secondary waves coming from different slits, n number of slits. So, the same way we have discussed for single slit, we have seen R is equal to A sine alpha by alpha for a single slit. And for double slit, what we have seen is R square is equal to 4A square sine square alpha by alpha square into cos delta, or we have written it in terms of, so we had a diffraction term and also an interference term. So here, due to n slits, what we are getting is A sine alpha by alpha, means all the rays that are coming from each slit having an amplitude A sine alpha by alpha are now going to interfere, and the resultant is given by sine n beta by beta. A sine alpha by alpha into sine n beta by beta. What is beta here? We have already defined beta, pi by lambda into E plus D sine theta, because the phase difference is given by pi by lambda into E plus D sine theta. So once you have R, we can calculate the intensity. I is equal to R square. So how do we get R square? A square sine square alpha by alpha square into sine square n beta by sine square beta. So this gives us the resultant intensity. So applying conditions on this will give us the principal maxima and the secondary maxima and also the minima. So what are the conditions for maxima? E plus D is into sine theta is equal to plus R minus n lambda. So on both the sides we are having, where n takes on the values of 0, 1, 2, and 0 is always giving us the 0 order maxima, or we call it as central maxima. N is equal to 0 will give us the central maxima, and n is equal to 1, 2, 3 correspond to the first, second, third principal maxima, or we also call them as secondary maxima. So n is equal to 1, you get E plus D sine theta is equal to lambda, or 2 lambda, 3 lambda, and so on. So for all these values, you get the maxima. And then what is the condition for minima? Capital N into E plus D sine theta is equal to m lambda, where m takes on all the integral values except 0, capital N, 2n, and so on. Why? Because for 0, we already have a maxima, so we cannot have a minima. So all these values of m make sine beta is equal to 0, which makes the principal maxima. So we will exclude these values and take this condition. Now it is clear that m is equal to 0 gives us the principal maxima. And for all values of m, 1, 2, 3 and so on up to n minus 1, we have the minimum. For m is equal to n, we are getting the principal maxima. So there will be n minus 1 minima between two consecutive principal maxima. That is what we need to understand. So if you see the pattern here, if this is the first one, this is the 0th order maxima, you will have another principal maxima here and another principal maxima here. So the intensity is given by sine square and beta by sine square beta. And due to diffraction, what we are getting is due to sine square alpha by alpha square. So if you see, as the number of slits grows, means we have drawn for, imagine capital N is equal to 15,000. We may also draw 25,000 lines per inch if the number of slits grows, the number of slits per unit inch. The peak becomes narrower and more intense. So here we are going to see the diffraction pattern for 5 slits. We have seen for 1 slit, we have seen for 2 slits, we are discussing for n slits. But if you are considering only 5 slits, this is how we are going to have. This is the principal maxima, central maxima, and these are the other maxima. And in between you have minima here. So m is equal to 0, plus 1, minus 1. On either side you are going to have the pattern. So what are the applications where we are using? Diffraction grating is an immensely useful tool for the separation of spectral lines. When you have to separate the spectral lines that are associated with atomic transitions, whenever we study the atomic structures and we will have to observe the spectral lines. So we use a diffraction grating. So sometimes this diffraction grating, we also call it as a super prism. So here the tracks of a compact disc act as a diffraction grating, producing a separation of colors of white light. Whenever you rotate the disc, what you see here are colors. That is due to the diffraction phenomena. Now, how do we determine the wavelength of a given light using a diffraction grating? We'll use a laser source and calculate the wavelength of a given light. In laboratory, if you have to find the wavelength of a given light, we are going to use the formula lambda is equal to 2.54 sine theta upon small n into capital N. This comes from our original formula d sine theta is equal to n lambda. We want to find lambda. So lambda will be equal to d sine theta upon n. Now here we want to find the width of each slit d. So d will be given by 2.54 upon capital N. How we are getting 2.54 is in 1 centimeter per inch. So if we are taking capital N is the number of lines drawn per inch. In 1 inch we have n lines. 1 inch is nothing but 2.54 centimeter. Because we are using the SI system here, we are not going to write it in inches. We are going to convert it into centimeter. So in 2.54 centimeters, we have n lines. So what will be the width of one line? D. Here is the width of one. So it will be 2.54 upon n. So when we substitute here for 2.54 upon n, we have 2.54 sine theta upon small n into capital N. So we are going to use this formula to calculate the wavelength of a laser source of light using diffraction grating. So lambda is the wavelength. Capital N here represents the number of lines on the plane diffraction grating. And small n is the order of the diffraction of light. What is the order of the diffraction? We may get first order n is equal to 1, second order n is equal to 2, and so on. Now how we are going to get it is, we are going to place the grating in front of the laser beam such that light is incident normally, and then we get the diffraction pattern. What we have understood now, because of the superimposition of the waves that are, the secondary waves that are coming from secondary sources, what you can observe is a diffraction pattern on the screen at a certain distance. Now this is how we get the diffraction pattern. We have a central maxima. Then we have other maxima, n is equal to 1, second order n is equal to 2. This is n is equal to 1 and n is equal to 2. So the central maxima followed by the other maxima, principal maxima of different orders. So the secondary maxima in the diffraction pattern observed on either side is due to the first order, second order, and so on. Now we will first measure the distance between the grating and the screen, and we will write it as capital D. So what we have seen here is the distance between the grating and the screen. This is capital D. And the distance between the central maxima to the first order on the left side is D1 and on the right side is D2. So if we are having, this is the central maxima, on the first side we will take it as D1 and on the right side we will take it as D2, and we will note the readings. The distance between the grating and the screen, this is capital D. So the important thing you have to note down first is capital D, how you are placing the grating and the screen, capital D, D1 and D2. And then we are going to tabulate the readings. What is capital D? Which order we are noting down? What is D1 on either side? Left side D1, D2. So from here we can get D. And then sine theta can be calculated using small d upon under root small d square plus capital D square. So once we get sine D, we can easily calculate the value of lambda, 2.54 sine theta upon small n into capital N. So here capital N is the number of lines per inch and small n is the order which we are talking about. We may do it for first order and second order. So calculate the value of lambda using 2.54 sine theta upon small n into capital N. So using a diffraction grating, so we can find the value of sine theta and then calculate lambda. So this is also one important application of diffraction grating. So thank you and see you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.